Assalamualaikum and salam sejahtera. My name is Muhammad Baruzaman Bijamat 2170174, the first presenter from our group. Today we're going to present about a suitable signal conditioning for our topic, which is vertical displacement measurement of a vehicle body in vehicle suspension system. So from previous presentation, we are choosing LT300 LVDT. The first problem about this LVDT is the output of the LVDT is an alternate current or AC waveform. It has no polarity. So from this diagram, you can see that the voltage output is positive, then negative, then positive, then negative. Usually, this AC output voltage is converted by suitable signal conditioning circuit to direct current or DC voltage that is more convenient to use. This AC voltage can be converted by using rectifier. Shafiq will explain about this after this. The second problem is the voltage output is too small. For example, we take LD300 model 300 have the sensitivity of 1.7 millivolt per 1 millimeter displacement. The range of this model is plus minus 300 millimeter linear stroke. So we can find the output voltage by multiply it to the sensitivity. So plus minus 300 millimeter times by 1.7 millivolt, and we can get plus minus 510 millivolt only. Thus, an amplifier is needed to amplify the voltage output.
The types of signal conditioning needed for our LVDT are one that converts the AC source into a DC source, and another one that amplifies the output voltage, which is why we are using the rectifier and amplifier. A rectifier is an electronic device that converts an alternating current which has no polarity into a direct current which has only one polarity or one direction. The process is called rectification as it essentially straightens the direction of current. A rectifier has two types of rectification, which are the half-wave and full-wave rectification. And in our case, we are using the full-wave rectification because we need to utilize both the directions of the AC source. A rectifier utilizes diodes to convert the two directions of current into one direction, since diodes only allow one direction of current. In this picture, we can see the configuration of a full-wave rectifier with an AC input. We have the four diodes placed in a bridge shape with a specific direction. Since an AC source has two directions of current, we need to look at what will happen in each direction to better understand how this works. Firstly, we have the current flowing in this direction. Because diodes only allow one direction of current, we have the current passing through only diodes 3 and 4, and no current is passing through diodes 1 and 2 since it is placed as such so that the current won't flow in the opposite direction. And here we have the situation when the alternating current is flowing in the other direction. We see that the current only passes through diodes 1 and 2, not 3 and 4, since diodes 3 and 4 are placed in a reversed position. We can see from both directions of current, the resulting output current is only flowing in one direction, and that is how the alternating current is converted into a direct current. The second signal conditioner needed for our case is the amplifier, since the output of the LVDT is small, and specifically we are using the non-inverting amplifier. A non-inverting amplifier amplifies the input voltage without changing its polarity. This is a diagram of a non-inverting amplifier. The positive terminal is connected to the input, and the negative terminal is the output, but it has the resistors R1 and R2 connected in parallel and grounded. The output voltage is equals to the input voltage times the gain, which is 1 plus R2 over R1.
For the signal conditioning circuit, we want to be able to obtain a readable data. The problem is that the output voltage is too small and is in alternating current. The first step is to use a rectifier to convert alternating current to direct current. Once we've done that, the output voltage of the rectifier is amplified from 510 millivolts to 10 volts. In this case, we use a non-inverting amplifier. The formula for this amplifier is output voltage equals to 1 plus R2 over R1 multiplied by input voltage. From the calculations, we obtained that R2 equals 18.6 kilo ohms and R1 equals 1 kilo ohms.
To sum everything up, as for our discussion, we use LVDT as our instrument for our vehicle suspension system. Precisely, we use LVDT LD300 series because it has the longest linear stroke of the LD300 series. It has the highest sensitivity and also the most suitable for the car suspension system. However, there are some problems might occur, such as the output of LVDT is an alternating current, which it has no polarity, and also the voltage output is too small. So to overcome, rectifiers are used to overcome the problem of AC output waveform, and the amplifier are used to amplify the voltage output. As for the results from the LDX3A signal conditioning, which it amplifies to DC voltage of 0 to 10 volt after being rectified from 510 millivolts. The non-inverting amplifier produces output signals without any phase inversion, also has a higher impedance value compared to the inverting amplifier, and also has a positive voltage gain. Data is readable after signal conditioning, thus no large errors should occur in the signal conditioning to receive data. The voltage gain AV is equal to 1 sum R2 over R1 is equal to 19.6 kilo ohm, which indicates in-phase output with applied input signal.